Welcome to this beginner-friendly crash course on PySpark, the Python library that lets you process massive amounts of data effortlessly. In the world of big data, tools like Hadoop and Spark changed the game. But when Python met Apache Spark, it became PySpark, giving us the best of both worlds, scalability and simplicity. Now let's understand how PySpark actually works behind the scenes. PySpark follows a distributed computing model built on top of Apache Spark. At the core, there are three main components. One, the driver. This is your main program where you write your PySpark code. It's responsible for converting your code into tasks and sending them to worker nodes. Two, the cluster manager. This can be Spark's own standalone cluster manager, Yarn, or Kubernetes. It allocates resources across the cluster. Three, the executors. These are the worker processes that run your tasks and return the results back to the driver. Every job you run in PySpark gets broken into stages, which are in turn divided into tasks, and those are distributed across executors. This architecture ensures PySpark can handle large-scale data across multiple machines efficiently and fault-tolerantly. In this section, let's unravel the core building blocks of PySpark: RDDs, DataFrames, and datasets. Resilient distributed datasets, RDDs, were the first abstraction introduced in Spark. They provide low-level control and are immutable collections of objects that can be processed in parallel. While powerful, they can be verbose and less optimized. Enter DataFrames, a more expressive and optimized API. Think of them as RDDs with a schema, like a table in a database. With DataFrames, you get a cleaner syntax and performance boosts thanks to Spark's Catalyst optimizer. Then comes datasets, a blend of both. They offer the type capabilities of RDDs and the optimizations of DataFrames. However, in PySpark, datasets don't exist separately as they do in Scala. So Python users mostly work with DataFrames for structured data. In essence, choose RDDs for more control and DataFrames for most use cases where performance and simplicity matter. Let's now visualize the relationship and differences between these abstractions. Now that we've covered the execution flow, let's talk about the heart of PySpark, RDDs, or Resilient Distributed Datasets. RDDs are the foundational data structures in Spark. They are immutable, distributed collections of objects, and they allow operations to be performed in parallel across a cluster. There are two main ways to create RDDs. One, by parallelizing a Python collection, and two, by reading from external datasets, such as CSVs, JSON, or text files. RDDs support two types of operations: transformations like map, filter, and flatmap, which are lazily evaluated, and actions like collect, count, and reduce, which trigger execution. RDDs offer fault tolerance through lineage, meaning even if a node fails, Spark can recompute the lost data. While RDDs are low-level and give fine-grained control, modern PySpark projects mostly use DataFrames for ease and efficiency. But understanding RDDs is key to mastering Spark under the hood. One of the most fundamental concepts in PySpark is the distinction between transformations and actions. Transformations are lazy operations on RDDs or DataFrames that define a new dataset based on the current one. These include methods like map, filter, and groupby. Nothing is executed when you call a transformation. PySpark simply builds up a plan of what to do when an action is eventually called. On the other hand, actions trigger the execution of the transformations you've defined. Common actions include count, collect, first, and save as text file. This lazy evaluation model allows Spark to optimize your job before execution. It reduces data shuffling and improves performance by constructing an optimized DAG, directed acyclic graph of operations. Here's a good rule of thumb. Use transformations to define your computation logic. Use actions to materialize the results and trigger the actual execution. Lazy evaluation in PySpark, one of the most powerful and misunderstood features in Spark. So, what exactly is lazy evaluation? In PySpark, when you write a series of transformations, like map, filter, or flatmap, these operations don't run immediately. Instead, Spark builds a logical plan, kind of like a blueprint of what needs to be done. It waits until an action, such as collect, count, or save, is called. That's when Spark decides to actually execute the plan. This lazy behavior may seem odd at first, but it brings two major benefits. First, it allows Spark to optimize the job. Spark looks at the entire chain of transformations and performs what's called pipelining, combining stages efficiently to minimize execution time. It's like planning a road trip with the shortest and fastest route before hitting the road. Second, it prevents unnecessary computation. If a transformation is defined but never used in an action, Spark skips it entirely. That means faster jobs and lower resource usage. Let's consider a quick example. Suppose you have a large dataset and you define a filter, followed by a map, but never call an action like collect or count. In this case, Spark doesn't do anything. Nothing is processed and your cluster sits idle. It only springs into action once you tell it what final results you want. So in short, lazy evaluation allows Spark to be efficient, smart, and scalable, which is why it's at the heart of Spark's performance advantages. In this section, we'll explore how a PySpark application actually runs under the hood, from the moment you submit your code to the point when results are returned. Let's break it down step by step. 1. Driver program. The journey starts with your driver program. This is where your PySpark code runs. It initiates Spark context and defines RDDs or DataFrames, transformations, and actions. 2nd, DAG creation. Once your transformations are defined, Spark builds a directed acyclic graph, or DAG. This DAG is an optimized logical execution plan representing the sequence of computations. 3. Job submission. When you trigger an action like .collect or .save, Spark submits a job to the cluster. The DAG is split into stages based on data shuffles. 4th, task scheduling. Each stage is then broken into smaller units of work called tasks, which are distributed across the cluster's executors for parallel execution. 5th, task, execution and results. Tasks execute the transformations on partitions of data. Once complete, the results are either sent back to the driver or written to storage. This entire workflow is optimized for performance using techniques like pipelining, caching, and intelligent task scheduling. Understanding this workflow is key to writing efficient and scalable Spark applications. In Spark, when we perform operations in parallel across clusters, each task runs independently, which can make sharing information across them tricky. That's where shared variables come in. There are 2 main types of shared variables in PySpark: broadcast variables and accumulators. Broadcast variables are used to efficiently share large, read-only lookup data with all worker nodes. Instead of sending a copy of the variable with every task, Spark distributes it once, saving network overhead and speeding up execution. A great example, when you want to join a large dataset with a small static lookup table. Accumulators, on the other hand, are write-only from the worker's perspective. They're ideal for collecting metrics or debugging information across tasks. For instance, you can track how many records failed processing during a job. Together, these shared variables provide powerful tools to manage distributed computation more effectively, reducing redundancy and enhancing performance. One of the most powerful features in PySpark is its support for structured data processing through PySpark SQL and DataFrames. A DataFrame in PySpark is a distributed collection of data organized into named columns, much like a table in a relational database or a pandas DataFrame. It allows you to manipulate data using high-level operations that are both expressive and optimized. You can perform operations like filtering, aggregation, joins, and more, all with simple syntax. And under the hood, Spark optimizes these operations for performance using its Catalyst optimizer. Even better, PySpark lets you use SQL queries on DataFrames. You can register any DataFrame as a temporary view, then run SQL queries as if you're working with a real database. This is especially useful for data analysts or engineers who are comfortable with SQL but want the scalability of Spark. This combination of SQL and functional programming gives PySpark a unique edge, enabling both flexibility and scalability. In real-world data engineering workflows, you'll often deal with different file formats like CSV, JSON, and PARQUET. PySpark makes it incredibly easy to read and write these file types at scale. CSV files are simple and widely used, but they can be inefficient for large-scale processing because they lack metadata and type information. Still, PySpark supports reading and writing CSV with just a few lines. JSON files are semi-structured and great for hierarchical data. PySpark can automatically infer schema from JSON files, but when it comes to performance, nothing beats Parquet, a columnar format optimized for read-heavy operations. Parquet files are compressed, splittable, and support schema evolution, making them ideal for big data. With PySpark, handling these formats becomes smooth and efficient, making your pipelines faster and more scalable. When working with large datasets in PySpark, performance can take a hit if computations are repeated over and over. That's where caching and persistence come in. Caching is used to store the results of intermediate computations in memory. This helps avoid recomputation the next time those results are needed, especially useful in iterative algorithms or when a dataset is reused multiple times. By default, cache stores the data frame in memory only, which is fast but limited by RAM. If memory is insufficient, the computation will be re-executed. For more control, you can use .persist with different storage levels. This will keep the data frame in memory if possible, and spill it to disk if needed. Caching and persistence can drastically improve performance when used wisely. But remember, overusing them can consume cluster resources unnecessarily. Always monitor your storage and memory usage when applying them. In summary, use caching and persistence to speed up your PySpark jobs when working with reusable data. It's one of the best ways to unlock efficiency. Efficient data processing in PySpark heavily depends on how your data is partitioned and how it is shuffled across the cluster. Partitioning refers to how data is split and distributed across the worker nodes. Each partition is processed in parallel, so more balanced partitions lead to faster execution and repartition if needed. Use repartition for a full shuffle and better distribution. Use coalesce if you just want to reduce the number of partitions without triggering a full shuffle. Shuffling is the process of redistributing data across partitions. It happens during operations like group by key, reduce by key, join, and distinct. Shuffles are expensive. They involve disk I/O, data serialization, and network transfer. Optimization tip: prefer reduce by key over group by key, as it reduces data on each partition before shuffling, which minimizes data movement. Also, you can use broadcast joins to avoid shuffling large tables. In summary, mastering partitioning and minimizing unnecessary shuffles is critical for scaling Spark jobs. The less you shuffle, the faster your job runs. Before we wrap up, let's quickly run through some of the most commonly used PySpark functions. The kind of functions you'll use daily in real-world scenarios. Data cleaning and transformation, functions dropna, fillna, used to handle missing data, drop nulls or replace them with default values. With column, one of the most used functions. Great for transforming existing columns or adding new ones. When, otherwise, conditional logic works like if-else for column transformations. Col, expr, used for column expressions. Handy when writing clean dynamic transformations. Data aggregation functions group, ag, grouping and aggregation, from simple counts to complex statistical metrics. Count, sum, avg, min, max. Core aggregation functions that get applied in nearly every pipeline. Working with strings and dates substring, split, concat, manipulate strings in columns, often used in data parsing. ToDate, date, Chonka format, data diff, crucial when handling time series or date-based operations. Joins and filtering join, essential for merging datasets. Supports inner, left, right, and outer joins. Filter, or where, used to extract relevant subsets of data using SQL-like conditions. Window functions row number, rank, dense Posh rank. Super useful for deduplication, ranking, and running totals within partitions. Over, window partition by, order by, adds powerful analytics capabilities. Think Excel-style advanced formulas. These are the building blocks of real-world PySpark workflows. Master these, and you'll be ready to handle 80% of daily Spark tasks with ease. Don't just memorize them. Practice, break things, debug, and build. And there you have it, a solid foundation in PySpark that'll set you up for success in the world of big data. We've covered everything from RDDs to DataFrames, from Spark architecture to hands-on functions, all the core concepts that you'll actually use in real-world scenarios. If you found this video helpful, smash that like button, and don't forget to subscribe for more deep dives into data engineering and Spark. Have questions or want to share your own PySpark tips? Drop a comment below. I'd love to hear from you. Until next time, keep learning, keep building, and stay data-driven. See you in the next one.